Sophie for the introduction, and welcome everyone, and thanks for joining. I'll just share my screen. Yeah, hope you can see the screen slides. So good morning, good afternoon, good evening from wherever you are, and thanks for joining. So let's start. Sophie has already introduced. I would skip this. So today's agenda would be, we would be covering introduction to firmware, and we'll look into why do we need firmware reversing, what are different possible attacks with respect to firmware. Then we'll look into some of the tools that you should know if you are getting started in this thing, and we'll look into some of the attacks which occur due to the vulnerabilities in the firmware. And finally we'll have some hands-on lab for which you have been provided with the virtual machine. So it's suggested you can download it and keep it ready by that time. Coming to firmware, it was coined by Asher Obler, and it was published in Datamation article. It's the magazine. So according to Wikipedia, it says it's the software that gives us the low level and that gives us the access to the low level of the hardware, and it controls, monitors of all the product system. In a simple terms, if I say, so all the smart devices, the whether it is smart camera or routers, these embedded devices that we are seeing around us have some software running on it, similar to the applications that we see on our PCs running. Similarly, those devices have some logic, some software running inside it that we call firmware. And they are mostly stored in non-volatile. They are stored in non-volatile memory, especially like flash memory. It could like mostly in external flash memory, and they run on the embedded devices. Basically, firmware are of two types. You can be OS-based firmware, and other is bare metal firmware. When we say OS-based firmware, it means we have a hardware. On the top of hardware, there is some OS running. It can be your Linux or VxWorks. So those OS handles everything and work and gives to the application level. But in case of bare metal, we don't have OS. We have hardware abstraction layer that deals with it, and then the applications are dealt. So when it comes to firmware reversing of embedded devices, we can face two different types. If we extract the binary, it could be either OS based or it could be bare metal. So question comes, why do we need to do firmware reversing? What's the requirement? So I'll take example of an IoT device, and this IoT device has a hardware, right? The camera, all those devices have those embedded devices have the hardware inside them. They have some user application with which we interact. They, for making the communication over the internet, they have a communication layer. Then we have some kind of management storage. These are complete linked into this ecosystem. So, and then to moderate all these things, we have some kind of logic given, the main business logic given to the device, that is the firmware. And in most of the cases, this firmware are sometimes like an IP for some vendors. And if it get out, it's a big business loss for them as well. So if you are or any attacker is successful in finding any attack vector or any vulnerability on the firmware, it could directly or indirectly affect the other part of the ecosystem. So for example, one point comes if the firmware is IP for some vendor and someone is able to get that firmware. In today's, we will be mostly talking into the basics of the reversing, but getting firmware could be from the different way. It could be via the hardware attacks or some kind of tweak, or you can also download it directly from the vendor's website. So if you get the firmware, and like if it's an IP, obviously it will not be available on the website, and you have to do it some kind of trick around the hardware hacking. And one way, if you get the hardware, you can clone the device, and it affects the IP. And another thing is, if you get the hardware and we perform reversing on it, it leads to unearthing of another exploits. So, for example, there could be something important, or when you reverse it, you will see something that can affect your communication layer, that can affect your management layer. Though they might be on the software, on the application, user application side, they might be developed very good, authenticated, but on the firmware side, if you find something, let's say hard coded thing, you can use it and break the system, break the other parts of the ecosystem. So when it comes to what are the possible attack cases, or what do we look when we do the firmware reversing, on how do we get? So today I would be, since we just have 2 hours, I would be focusing on the firmwares, basically OS based firmware. And when we are able to get the firmware from any device, the binary, and if we know how to deal with it, we can look inside the file system, we get the complete file system. After getting the file system, we can explore and for any custom binaries that may be exploitable, we can look for some hard coded sensitive information. So for example, some any, let's say some MQTT protocol is running on an IoT device, and it has some authentication, and you need to log it for login. If you are reversing the firmware and if you find these hard coded inside the firmware, you can directly use the credential to break that part. Similarly, you can look into configuration files present inside the device. You can look for if any certificates. You can perform debugging. It could be either hardware or software. And even if you don't have the hardware, but if you want to deal with some kind of analysis, you can do emulation. Then the case comes, you can fuzz the device, that we'll see in next slides. And you can also look for different vulnerabilities, that could be remote code execution, command injection, DOS attacks. And in fact, if the secure firmware update secure is not implemented securely, there is possibility that you can patch the firmware with the backdoors. So there are different cases when we get the firmware and we look for these things, through which way can we enter the system. So coming to introduction to tools, for, well, looking into basic tools that we at first require when we deal with firmware static and dynamic analysis. So what's the approach if we get the binary? First, we need to identify whether the binary is OS based or bare metal. So if we know from which device of which device the firmware is, we can identify its which type of firmware is it, whether it is OS based or bare metal firmware. So if you have got that firmware from any microcontroller based, so mostly it could be bare metal, simple, that is having like and then if you have some heavy applications, camera, routers, it could be OS based firmware. So we need to check that. Then we have to check whether the firmware is encrypted or not. In case the firmware is encrypted, it's get bit tricky to deal with it. So first, before getting into the tools that I would be talking today, we need to work around to decrypt that firmware. And there are different ways. It's very tricky, but there are different ways. One could be, in some of the cases when vendor release the firmware, there are transition versions. So though there could be one final version which is completely encrypted, but there are chances that in the transition version, you can find its encryption algorithm which can be reversed, and that could be used to break the encrypted firmware. Another thing goes to getting the keys via hardware attacks, like SCA here is side channel attacks to get the key. And there are also many different ways that people have worked on, like analysis of the patterns on the hex editors, Binwalk tools. So first, if the firmware is encrypted, we need to decrypt that thing. And other the cases, if the firmware is of bare metal or RTOS based, or if it is something proprietary for which most of the tools are not working out, in that case also it gets we don't have much tools in our code. And in that case, first we need to identify what the controller running on it, what we have to take the data sheet. We After taking the data sheet, we generally identify what is the architecture, we map the memory, And then accordingly we load in any disassembler tool like Gaidra, ITA Pro, and most of the like manual reversing goes some of the using some plugins that help us out in somewhat automation. And sometimes it can also be done using partial emulation using Unicorn or Kemu. So yes, if you have a OS based firmware, we can get ready with the tools and start. Coming to static analysis, in case of static analysis, it's basically you are not running that firmware on any device. You just have the binary and you have to do you are simply extracting that what's the file inside it. You are trying to find if some kind of interesting strings, you can look into it. Then you do the hex term to identify if there are some common patterns that you can check that can give you a hint, some file signatures and so on. And then you need to identify if in case you are unable to identify through standard tools, you need to bit of look into the assembly codes to understand what the instruction set could be on the device. In case of dynamic analysis, we have emulation. So what happens, the first phase when it comes of static analysis, what we do, in that case, we get the firmware, we analyze it, we check, we load it in any disassembler, and we look for any hard-coded data, we reverse some algorithms, then that gives us somewhat idea that possibly this could be the vulnerability in the device. Now we need to check that whether what I am assuming or what my research says, is it correct or not. For that, obviously, you need to run the attack on the device. It could be possible that you don't have the hardware with you in your hand. And in that case, emulation works. So for example, if you are running some network camera, or you have the firmware of any router, and after reversing you found that it could be some xyz attacks possible after reversing, I find. And then what you can do to implement that, you can simply emulate that. So we'll look into the what are the different emulation tool that can help you out. Then comes fuzzing. So you would have seen that most of these network devices have some kind of user interface, could be web interface or app interface, via which we need to put in some user data sometimes, like login password or any kind of data that user has to enter. In that case, what we do, we try to check, is it possible that we can put it any random data and the device get crashed sometimes, or is it doing proper sanitization while accepting the input from the user. This gets the another attack point. And then other thing gets, when we do dynamic analysis and via debugging. So if we have the hardware, we can do the debugging using GDB by connecting it to hardware, and like through the normal GDB operations that we do. But in case we don't have the hardware, what we do the emulation, and again we debug it via GDB after the emulation is set up. So we can do both hardware and software debugging to this gives us better idea at what stage what kind of registers are being dealt. It gives a more in-depth understanding. So coming for tools for static analysis, it's the one of the basic tools is Hex Editor. So when we are given the binary of any like the firmware binary, so we generally run it with Hex Editor to identify if some kind of file signatures could be found, or if we can find any patterns. So if it is encrypted, you might find some patterns inside it. If not, it could be some random thing. You can also use strings to get if any strings present in the data, just strings command and the binary file name. Next tool that is important that should be with us is Binwalk. So this helps. It also would not be very useful if our firmware is from bare metal or encrypted. It's useful when we have OS based and not encrypted. So most of the time it gives a very like we can know by via its entropy, we can know whether the firmware is encrypted or not. So if so its entropy range from 0 to 1. So if we run binwalk dash capital E and the file name, and the entropy graph shows complete linear on the top of near to 1 something, so it means it's encrypted. If we run again on the some binary, and if there are some spikes in between, it means there are some part which is not encrypted, and it means we can get something out of that binary. Similarly, Binwalk can, if Binwalk small dash e you do, it can completely extract your file system, whatever is inside the binary. So let's help you in getting your file system. So similarly, there are different features that you can look and play around with the Binwalk. Next tool is Gaidra. So Gaidra is it's good because it's open source, and it has a very good disassembler. So even if we are not very comfortable with assembly language, because it could be some of you might be very good at x86, or some of you might not be knowing or might not be comfortable with assembly thing. But it's so there, this is how it's look like. You have these symbol tables, and this main where you see the assembly part. Then you have this disassembler where pseudo C code, I would say, you can be able to see like much readable pattern, and it gives you a good, it's a very good platform to reverse if you want to reverse any um, binary. Another thing is IDA and Radare are obviously the other options. Our next tool is Firmworker. So this tool, uh, as I said, while doing static analysis, we go through different files in the file system to check if there are some hard-coded credentials. Are there some configuration files or any certificates that we can look? So there is one way we go inside the file system. We'll look every file manually, one by one, to identify our attack point. But the Firmworker helps you in identifying the location of these files. So if it does not find any of these certificates, it will not give you any result. If it find that there are some important binaries, it will give you that these are the binaries that are present uh, inside your file system that you can probably look at. And similarly, there are what are the different web servers running, what are the possible password files present in the file system, so that you do not need to look at you not do not need to look and trace manually everything. It saves time. Facto, this I haven't used personally, but it has a good web UI, and it has in backend everything, the Binwalk, everything, and it gives you all this. This is somewhat this entropy graph that I was talking about. So if this graph is spike is this near to 1 always, this is like encrypted, and if it has some spikes, it means you can get some data out of it. Similarly, it gives you all the file path and everything. Another is exploit firmware auditor. And this also has almost the same feature as this fact. It has the binwalk in backend. You just have to load your binary here, and you get the entropy graph. You get all the file system related to it along with their path. So if it is your password file, it gives you where your password files are located. If it is your configuration file, it's give where exactly your configuration files are located. So these tools helps and saves our time in manual analysis. So these were the tools that I just discussed. So if there are any questions before I move.
Yes, Asmita, there is a question, and question is, when sniffing high-speed buses, what tools do you recommend?
Sorry, can you please repeat the question?
So the question is, when sniffing high-speed buses, what tools do you recommend?
So that comes mostly into hardware part. Yeah, so this is actually where today discussing about the firmware. So when again it comes to this sniffing of buses on the hardware, it gets so you need like logic analyzer is one thing, but if again if it's very hard, it is not via the logic analyzer or via the this oscilloscope thing. Uh, on something related to this workshop question.
No, not yet.
Yeah. So basically, these were your static analysis tools. So this tool helps you in getting some basic understanding or something that you can use further to attack your device. So you can keep the point for any hard coded things or any suspected binaries that you see, or if any configuration file that could be patched. If the let's say in the one of the Firmworker example, we saw some of the service like SSH telnet that can give you the remote control of the device. If those services are running, they form your attack vector. So there is one case you can either tamper with that, or if the on the hardware side firmware update security is not properly implemented, you can change the binary and then patch with it some. If the telnet is, let's say, disabled, you can enable it and then patch with the vulnerable binary in the hardware to get the remote control of the device. And but if in that case proper secure boot and implemented, this won't work. Similarly, you get after analysis, you might see after analysis in tools like Gaidra, you might see that whether while accepting the input from the user, whether proper length checking is done or not. Then it gives you idea. If it is not done, then you can probably go for attacks like buffer overflow and check that out. So analysis and reversing via these static tools give you a base, I would say, for your further attacks. Coming to our dynamic analysis. So yeah, once once we get idea of our attacks via the static tools, we now look forward to perform our attack. So for that, sometimes static tools don't give a very better approach. So in some cases we want to know that what happens when I am when such function or when such thing is running on my on this firmware. When this stage is coming, then what is happening on the register side, which register is loaded, or what values are being disturbed. So in that case, you can perform dynamic analysis by GDB. So if you have hardware available, that gives you a very good surface that you can directly interact with the hardware, play around with by setting its registers and check the behavior of the device. Other, you can perform software debugging by emulation and then attaching it with a GDB. Another important tool is Chemo that helps you in emulation. And it's so it Kemu has two emulation mode, like user mode and full system emulation. So in case of full system emulation, you need to have those all kernel images and all, and it gets a bit heavy. And in case of user mode emulation, you can directly the firmware that you have extracted, the binary that you have extracted, you can directly go inside that file system, and you can put your Kemu Kemu executable inside it and directly run a one particular binary. You do not need to load all the kernel images and everything. Next thing is Avatar. Avatar is a very good tool that helps in dynamic analysis. How? Because when we emulate any firmware, it's obvious that we need something that can support its hardware too. So it gets a very challenging while during emulation, that we don't have like so much support for all the hardware that is available on our device. So Avatar helps us in providing those support. So this is one thing that could be very interesting to and helps in dynamic analysis. Next is Firmadine. Firmadine is based on top of Kemu, but it reduces our work. It also, like these tools, is not like they'll work on everything. So we need to sometimes play around. We get error on many things. We need to fix those issues and then get our things done. So Permadyne is one of those which helps again in emulation and you're performing the dynamic analysis. Unicorn is based on KEMU, but it just performs CPU emulation. So thing is, on KEMU, you can just emulate. You cannot perform or develop your own tool to perform the analysis, or you cannot do patching or something on the run. But in case of tools like Unicorn and Chilling, you can directly develop your own scripts, your own tools that you can have like run on the fly and check your thing. And plus, they have different like cross platform plus multi architecture. So in case of KEMU, if you are let's say doing user mode emulation, so if it's a Linux based OS, then only it will run on this your KEMU user mode, because when if you go in its more detail, you will find how it's forward the request from that virtual environment to the system host. But in case of Unicorn and Chilling, they can run on like they are all multi architecture plus multi platform like Windows, Linux, anything. uh, and coming to chilling is based on Unicorn, but it supports also system level emulation. So in that case, so Unicorn does not understand high level system. So if you wanna implement at register level or just a chunk of your code, you can do it via Unicorn. So this is very good tool if we wanna emulate something like our bare metal, which is not having the OS. But for that, we need to be thorough with the registers responsible for particular function inside those devices, and that this helps for those emulation. And similarly, chilling helps you emulation OS based. It has like system level understanding, and you can in fact perform on the fly. It has very good like plugins and all that you can perform all on the fly your attacks and check. You can patch on the fly. You can identify the address and do modifications onto it. Apart from these tools, we need some kind of fuzzing tools that I was discussing. So there are different types of fuzzing, like it has dummy fuzzing, then you have coverage guided fuzzings. So basically, tools like Redumsa, what they do, you give them the input, they will mutate your input. So you can simply, instead of providing random input manually, these tools helps you in mutating and providing random amount of random length or random type of data to your input to the system. So when this works, let's say a scenario. Let's take a scenario. We got a binary firmware binary of a camera or a router, and we via static analysis we were able to extract that. We got into its file system. We identified the binary which is responsible for running the web server. Let's say it's running HTTPD. We opened that binary in tools like Gaidra. We performed some kind of static analysis, like reversing on where is it, and looked for some of the important system functions inside the binary and checked how it is taking input from the user. Then we check like whether it is properly sanitizing what it is taking from the user. If not, then that becomes the possibility that if I give the input random to this thing, this may crash the device or this may lead to some kind of exploit. Then we move forward. So if we have the hardware, we can directly run the power on the device, run the server, and perform our fuzzing attack. If we don't have, we do the emulation, and then like so for example, let's say if you there is a section where you need to provide username, password, or any kind of logging from the user. You sniff the communication between the web server and the device that is communicating, and using tools like bobsuit, the web communication, you got the packet pattern, that which type of packet is being passed. So you take that we take that input as a sample, then provide it to the tools, let's say Radamsa. It will mutate that input, it will mutate that sample, and then we throw back that sample to into the input side to check that whether the device is having any effect by throwing back any random types of data. Similarly, we have other tools like AFL. We have more coverage guided tools. So this fuzzing and emulation gets more. They are very good when we are doing when we are performing our exploits on the firmware. So coming to attacks. So basically, the attacks which I will show now would be with uh, show how these analysis results in this type of exploits, the vulnerabilities. So, in order to reach these vulnerabilities, we need to start somewhere. We need to start somewhere. So, today in the lab session, we would uh, check, we will perform some of the basic labs of how to start so that we can reach to this thing. So, coming to our first example, the CV20178 that is the command injection. And I'm sorry, I think I missed this CV. Please correct that. This CV is 2019155530. This would be the CV here. So this CV. So basically, this was found in the router D-Link router, and it was a command injection attack. So what happened? The attacker found an HNAP. This is the home network, this protocol that's used in these type of devices, cameras and network devices. So inside the file, bin go ahead, there was API HNAP API function. Inside that function, the proper input sanitization was not done, via which the attacker, if able to control that thing, can pass any type of command to the system. So, for example, uh, in this was taken from this of the article. This was sniffed when the communication was happening, and during sniffing, as you can see here, some kind of username and like password was being there is being taken forward. So after so this is what I was telling when I was telling sniffing from the bob suit. This is taken in the bob suit. So it gives you what the packet is passed when you come when your device is communicating with your web application. So you get some kind of input pattern. So for example, you can further take this input and give it to Radamsha. It will mutate it and you'll forward this packet. So, but in this case, they found that this thing was being passed at the as a username and login. So, if uh, it was reversed, this go ahead of binary was reversed, and inside that HNAP API function, it was found that when the input is taken from the user. So this is a MIPS architecture, this MIPS instruction set, and these A0, A1, A2, A3, A4 are, you are saying it's the parameters that is passed to the function. So if you check here, there is a system function. So the system function that directly act your, like it says open file or any command that we run on the system. So these functions used for running those commands, and by passing the argument to this system function, as you can see, it's directly accepting from the address space and without any input parsing. Like there is no check that whether proper length is what is the length of input that is taken, or if there kind of character that should not be accepted. So this no checks are being done over here. It's directly accepted from the user and passed to this system function. So if such type of implementation is done in the firmware, it can lead to those attacks. So if, for example, as a user, if it can pass any length of function or any command, and since there is no checking that whether it is slash or any kind of those no character checking, neither the length checking, then it can execute any functions inside it. And this can lead you to the attacks like command injections and all. So, so similarly, if so, so how do we reach to this attack? So before getting this, we need to get the binary file firmware of this device, right? After we get the firmware of the device, we need to perform our static analysis from the tools that I discussed before. After performing the static analysis, we like when we get the file system, we go around the file, we find the binary that is interesting or the web related. Basically, the target goes to web related binaries. So we found that okay, so there is some go ahead binary running inside it. We opened that binary inside the Gaidra. Then from Gaidra, like any disassembler tool of your choice you can use. So you use this in your the disassembler tool. You find like you reverse these instruction sets, and then identify what could be the possible flaws, and you find that okay, there is we look for system function is being called, its argument is taken and it's accepted, but there is nowhere any input parsing check or any kind of sanitization being done. It means if I pass any command, it should be acceptable. Then you check from the verb suite, you take that and you start performing your attacks on the device. If the device is available, you do directly on the web, otherwise you emulate and perform that attack. Another comes the CV2020861 Pro. It was a remote code execution on ASCII device. It's also a router, and basically it's a Wi-Fi extender. And in this case, if you see, it has two vulnerabilities. One was it had a FTP server running, and that has a hard coded credential that can be used by any attacker to load any malicious firmware. And another thing was they had some service running, and there was flaw in that service that could be exploited. So see, to reach to this point that this could be there, we need to like all the basic steps that I discussed remains the same. And all the things that remain further is how do we if someone is having experience in binary reversing, maybe it of any architecture, then this part gets very easier once you are clear with what you have to do in the start. Then you have to reverse and perform your reversing steps. So if you look at this, it was the CGI files that are generally used in this web application. So inside the CGI file, there is just a system command. It's taking the file and storing at this space. So when taking the file, this thing was its hard coded credential as username and the password over here. So this can directly be, after reversing the binary in any tool, this can directly be seen by the attacker, and he can use same credentials to perform any attack or load any of the malicious thing. Plus, some of this thing had a right to perform uh, like changes in most of the directories of that server, and that can help the attacker to perform any kind of backdoor manipulation and implant his or own firmware inside it. In fact, by loading the firmware in this case, no signature check was being matched. So any file that was loaded, and since the credentials are already hard coded, this can be used by the attacker to load any malicious firmware. Another things come the service. So basically, when any device is running, it has some kind of services running. It could be your telnet, SSH, or any related services running on the device. So similarly, on this case, there was some BD SVR running. So it's accepting the communication, listening on this D3AC, that is port 54188. And it was after the reversing, it was observed that once this socket was created, and then it was waiting in a while loop for the connections, and inside those binaries there were different functions that were susceptible. So when we do the reversing part, we look for these such either web related binaries that are there where we have the possibility to attack, or some kind of custom binaries, or when we perform the network scanning, we see some ports running on the device. So that helps us in identifying if there are some ports that are not standard or very strange type. That gives us the idea that there might be some custom services running inside it. And then we look and search for that binary file inside the file system, load it in the disassembler, and then look for different functions or attacking point inside it. So they were having similarly some command, send, read, write applications. So when it was observed, then it was observed that these functions were calling system level uh, uh, system level functions. So like a file related, write, open directory. It means it these functions can help the attacker to directly interact with the file system of the device. So after further observing, reversing these functions, it was observed that if a certain pattern of input is provided via this function, then they then those functions were accepted by the device, and it could be able to write used by the attacker to send any kind of crafted input. So this pattern was identified, and similarly using simple Python script, once the connection was established on that port, then this the message in the similar crafted pattern. So it has a magic signature. So it was sent over here, this magic signature. Then similarly command type, payload, and then finally the custom file content. So the pattern remained the same, and we five sent our custom file system. So this case, by reversing the binaries, the attacker was able to understand what kind of input could be accepted if it is waiting for some kind of connection, and it was reversed, and similarly crafted input was sent that was accepted and executed. So again, uh, this is how the vulnerability in the firmware can help you in remotely attacking or taking control of the device even remotely. We have our next example, that is buffer overflow. So this was found in the TP-Link router, and it was running. It has the HTTPD binary. So so when it was observed, it has the pattern remained the same, like extracting the binary, taking it in the disassembler, and reversing part. So it had a function called that was handling the string, and inside it had like destination, size, source. So and there was several escape characters that it was escaping there through. So this same function was called inside another function which had this string modify. Same function was called inside this write page param set function, and this function was generally used inside user rpm function to print some value that is passed through get. So when as a get parameter is passed, so whatever the value is passed, it helps in printing. So all this write parameter write page param set was called in this function. So if you check this, it has a request value. So it accepts the request, and this the value of the buffer. So this same buffer, this value is passed over the string modify, and the string modify is the source. So this becomes the source for that string modify function, and this is the destination is, and its buffer size is 512. So this is the destination, this is a source, and source is, if you see, is has having the size 68. So size is 68, the buffer is of destination buffer is 512, but think if you say it's the size character. So this decides, so how this function is working. It either stops accepting until it encounters the null character, or the size byte is consumed. It has two way to stop accepting the input. So when it comes to this, if you see, the size to which it will stop is 0x200. If you convert it to decimal, it's 512. It means the size, acceptable size, and the size of the destination is same. And though the size of input buffer is 68, So there is nowhere size check of what the size of the value, what the value, this source size is being sent by the user. So though it could be, it means if it is having, there is no check, there is no string modify, it's stopping only when its size is reached. And in this case, size is same as the destination 512. It means though it is 68, but even if the attacker provide any large number of any large size of payload, it could be until this 512 or null, it would be accepted by this thing. So this is how another this gets the buffer overflow. So those the buffer size is just 68. You can, any size length could be accepted over here. And this is another example. So it's more in on the running services side. So in most cases, during debugging or during development, developers have this keep telnet or SSH open for their purpose. But when it comes to production, it's always recommended that these remote accessible ports should not be left open. So in this case, it's the shaker endoscope that generally used to like look into such system which are cannot be reached by human. So in medical devices, in garages, these devices are used. So what it does, it though since the telnet was enabled, attacker could directly connect through its network, and using that telnet service running, it can get the remote access of it. So this is how so coming to, though authentication could have been implemented, but the taking credential for these services, it is not that tough. It could either be brute forced, or it could be, if it is hard coded or it is set default, it could be reversed via the firmware if the firmware is accessible. So this is how the vulnerabilities in the firmware, though we are seeing it being attacked from the application level, like via the web application we are attacking, or via some services we are attacking. But to reach to this attack, we need to come from the bottom to top. After the binary, we need to perform those static things, then we need to actually identify what should I attack. Though we know these are the possibility of attack, it gives us a somewhat better hint that possibly if I can find some functions like system and all while disassembling or while reversing, that could be my point. Then if I find some kind of system related function, then I need to check that whether the what kind of argument is being passed to that. Is that argument such that that is accepting from the user, or it is not, it is not related to user anyway. And in case it is accepting from user, then whether those length or proper length check is done or not, proper character acceptance check is done or not. All these things matters in our reversing. And then once that gives us the idea of possible attacks, we come to our dynamic analysis to perform our, if we do not have the hardware, we perform the emulation and first that part. And that is how we lead to these attacks thing. So I'll so we'll go with the labs if we have any question. So basically, since we have the introductory part of the firmware reversing, we'll go, we'll practice, we'll have some hands-on practice on those, how we, what do we do, we get just a binary thing. So if we have question.
Yeah, I believe all the questions are answered by the fellow attendees, but still I'll ping in the personal chat some questions I gathered. Just have a look.
I've got a few of the questions captured. So one of the early ones was just asking about what the entropy graph was, and specifically what the entropy being referenced there was relative to. There was some discussion in the chat, but if you want to weigh in on that.
Yeah, so when it comes to entropy, entropy is basically randomness in the firmware, or randomness of anything of which you are calculating the entropy of. So when we calculate the entropy of the firmware, we see the randomness inside it. And the graph that that's the that is obtained by that Binwalk, it gives us the randomness which is present in that firmware. So if it is more random, probably it's more encrypted thing. So if we have a binary and we do normal strings on it, and we get a very gibberish type of thing that we cannot be understand by normal human, it looks something very random. It could be its entropy would be high, and it means it could be encrypted. But if its entropy is low, and it means it has less randomness, means there's something that is human readable. It means we can probably extract it and get something out of it.
Cool. Another one that came through was, are these tools analyzing ELF binaries? To what extent are they disassembling them? And then further, can they be used to look into Arduino firmware, or would different tools be used for that type of inspection?
Yeah. So basically, uh, uh, for this Arduino type of firmware, it's more of bare metal firmware. So it does not has OS into it. So any any application, any firmware that is running having either RTOS, real time OS, or normal or just without any OS, like bare metal thing. So those things can you, for that thing we need to know a bit more detail about, let's say Arduino. Arduino is having a controller AVR. So for AVR we need to know the AVR memory location and its AVR architecture, and then you can directly load that binary in Gaidra. So in that case, your Binwalk will not work. So Binwalk does not support those type of firmware. It works when you have proper OS, Linux or any VxWorks type of OS firmware. So you can load it in Gaidra. And in case of disassembly, when you say to what extent, it does not give you the exact like the source code thing. A pseudo code thing, pseudo C code that helps you in understanding what is happening. But still, for some of the bare metal thing, for example, STM and all, there are plugins called, for example, SVD loader for Gaidra. Since I have used Gaidra, I have not used and somewhat to Radare also, but I have not used IDA Pro, so I'm not very sure what's the functionality of IDA Pro. But for Gaidra, there are plugins for those things. But still, there are, in case of bare metal, we have to do a lot of manual reversing. Like if we see any register value, we need to take that value and go back to the data sheet and match that what this register is corresponding to. So for example, in your Arduino, you are running blinking LED code and you try to reverse that thing in your Binwalk will not work. You have to load that in Gaidra. Then in Gaidra, you when you do, if you are good with assembly, it's very helpful in reversing always. Like I would always say, if you are at least have a good um, go through with any of the instruction set. In IoT devices, most commonly used are ARM and MIPS. So you look into the Gaidra and you see those register values and then match. It will not give you like exact what this do. We have to go back and check ourselves.
And then kind of to bundle a couple together, and there was some discussion in the chat about this. Can you put a bit of the process in perspective relative to kind of time in getting started? So, you know, kind of the thing itself, beginning to look around, and then how long, you know, days, weeks, months for some of this vulnerability inspection.
Can you please repeat? I think voice broke and I didn't get the question. Yeah, can you please repeat the question?
I think that the at least last part of the question was about how long you would generally expect this kind of reversing process to take, like hours, days, or weeks.
Yeah, so it depends on what kind of firmware we have got. So if it is encrypted, it takes time, like weeks. But if and in case of if it is not encrypted, just the decryption part, and in that case it takes few days. If we are good with, like, it also depends on how much like we are good and experienced with that part. But if it is encrypted, it really get tough to do stuff.
So I just had one small comment as well, not so much a question, but a comment. You were talking about input sanitation, or input sanitization, maybe. When I've been reading about this before, I've seen a point that might be helpful, that sometimes it might be useful to think of it as rather output sanitization. So when you get input from the outside, the network, for example, where you actually output that to other things, like, for example, the system call and things like this, or SQL queries or something like this, where the sanitization is very much dependent on where you send it, if it might be useful or attackable.
I assume the question says, like I talked about the input sanitization, and how about the output?
Yeah, it was just a small comment that sometimes it might be helpful to think in terms more of output sanitization rather than input. Not a question, but more a comment.
Yeah, that could be, again, I think that could be other way around. So before passing whatever we are taking from the whatever we are taking from the input, we can further we can do it on other side, before accepting the input, or after accepting the input from the user. Like anything before passing to any critical functions like system, we should sanitize it. It could be on either side. So we can go with lab, sure. So yeah. So I hope everyone is set up with the VM. I'll just share my VM screen over here. So the first lab would be to identify the firmware. Like, you will be given in lab 1, you will be given the binary, and we have to extract that binary. We need to look into the file system, and we have to find the telnet credentials inside it. So I'll just share my VM. Yeah, I hope you all can see my VM. So inside this folder, you have lab. You go lab, and we'll go with this lab first. So this is the binary file which we have, firm lab 1. So our task is to extract this binary first. So before running any to get the information, you can either do any hexterm or random strings to get some data. You can run file command if you get something. Nothing much. You can check with Binwalk that I was talking about. So if you do just Binwalk and data file name, so you see something like you get some squash file is present over there. So there is something inside it. So the entropy that I was talking about, we just do Binwalk dash capital E and lab firmware name. So you get some graph like this. So there is you see here, there is a spike here. The everything is high, but there is something which has the low entropy. If I expand this thing, so this is which is having, so it varies from 0 to 1. So 0 means it is less random, 1 means more random. It means this part are encrypted or compressed, but this thing is accessible. It means even a part is accessible. It means we can file at least some file system inside it. So we'll try to extract this file using Binwalk dash small e and the file name. So if you look, you will see some directory inside it. Just so if anyone who is able to reach, please like who has problem, please mention in the chat. Who has not extracted till here? So if you are successful in extracting, if you look inside it, you will see the one of the file systems. Like we have different file systems in a Linux firmware. It could be GFFS, SquashFS. So we have this SquashFS file system. We can go inside this file system and you can see the whole, just clear. You can see this all the Linux file system that we generally see in our Linux machine also. So this file system is from inside the device of which the firmware is. So now once we are successful in extracting the firmware, so for extracting you have to keep dash small e. Binwalk dash capital E gives you the graph, or Binwalk dash small e extract this file system. So once we are successful in extracting the file system, now the things come, what could be the architecture or what the, so the some of the important binaries we generally find in bin directory. We can directly do ls./bin and you find this binary. So we can do file command on any of this binary. Let's do on busybox. And it gives you what architecture it is having. So it is having MIPS architecture. So now our task is, we have extracted, we know its architecture is using MIPS. Then our task is to find telnet credentials inside it. So if anyone, like after extraction, it becomes a bit easy. So if anyone is able to find this credential, please do post in the chat, but I'll continue here. So to find, since we know, since here we have been given the option, I have told you that we have to find the telnet credential, it's get much easier. But in some cases, we don't know what credentials do we are looking for, what service. So in that case, you can either do grep on many things, or if you are able to run the device and you can scan the network, then in the network scanning also, you can check what services it is running. Or so it's, let's just do grep on the file system. We'll check for telnet. So coming to telnet, we have find these sources. So this script, this is the script file that is having the telnet related services. So we can directly go to this file. And then, so this is the script that is responsible for, so init 0.d, as we know, like most of the startup scripts file, that the scripts that run during the start are inside this. So it is having this script file. Now I think you all can identify what should be the credential for telnet. Let me check the chat if anyone identified. Squash gives me command not found. For what purpose you are using Squash? Yes, Justin is right. So if you would have extracted, yes. So if you would have extracted using Binwalk, you don't need like you already get this Squash file system, the directory, so you can directly get into it. Otherwise, if you want to extract it, then you have that unsquashfs. But if you do through Binwalk, I don't think you need a squashfs thing. So coming to this, you can see, as most of you have already found it. So if you check inside it, you see something login and then -u. This is alpha network. It means your username is alpha network, and it means colon means it should be password. And this is $, the variable. So we can check what this variable correspond to. This variable correspond to this file. So we can go and check what's inside this file. Sorry, it should be dot. Yeah, so here you got the password. So this is how things are. So if the services are running and you and we are able to extract the binary and we find such hard-coded credentials inside it, so they can be now used for to take the control from the remote level. Can we get written? Sure. After this lab, by sharing the slide, what I'll do in the slides, I'll write step by step what I did in the lab. So that could be more easier for everyone to, maybe if later you want to try on yourself with yourself. What's the best way to hide this? Okay. So this is always, don't store it hard coded. Like what's the purpose of storing, like in fact it's so simple plain text thing. So it's never recommended in the binary that though you are developing your application, it's never recommended to store anything in the plain text. You either keep it encrypted, and then the encryption key is stored in some kind of more like trusted platform modules that could keep your key secret, or implementing trust zones that can keep your things secret. All right, so we can move on to our next lab. Just a second, I'll share my, yeah. So in the next lab lens of firmware modification and repacking. So in that case, so as I have already told you that if the things like proper signature check or secure boot is not implemented, it is possible that we can extract the firmware, we can do the changes and flash back the malicious firmware. So we'll do this. But for flashing back the malicious firmware, we need to know how to repack that extracted firmware in the binary back into the binary, right? So yeah, just so coming to our lab 2 folder. Here is the binary, and our task is that we need to extract the binary. That I think now you can do it yourself from taking help from the previous lab. After extracting the binary, you can do changes anywhere you want. So some of the files like password files or shadow files that contains the file, you can do the changes. Then we will make that binary to pack back in this .bin file, because when we flash the binary into any hardware, we need binary .bin. We cannot flash the directory inside it. We need the binary file. So we'll simply extract it. We'll go back. So again, it has having this specification, and then we can go into any file to do any changes you want. It could be in any configuration. So let me do in the password file. So cat./etc. So there are shadow files that keeps the password. So I'll just do shadow. So it is having this thing. What we can do, we can just do any random changes. So let me do sudo vi. So I'll be doing changes here inside shadow file in the etc. So let me add anything in the start. Let's say ZZZ. So I have just added this random gibberish thing inside this password. We'll just save this. All right. So now if you see, so now you see this is what we have changed, the password thing. We have changed. Now our next target is, though we have changed, what to do with this thing. We need to repack it and then do the change. So for this thing, so for this thing, we use the tool called FMK. FMK. So instead of Binwalk, so Binwalk helps us in extraction, giving all this forms file system. So what happens when we there is a tool called FMK, Firmware Modkit. So it has that we have already installed in this virtual machine. So you can directly run a command called extract firmware.sh. So that Binwalk thing did be just the revision thing that you extracted and got the thing. But after doing thing, how do we pack? We don't have, like, we don't see any way to repack everything. We have this directory, but we cannot flash back this directory. So for that, we have this Firmworker. So instead of Binwalk, for this case, we use FMK, which is having this extract firmware.sh and the binary name, not the directory, binary name. So if you do this, it do the unpacking in a folder called FMK. So it's take few seconds. So in shadow file, I just did anything. So you can change any file for your reference. So the main target of doing this lab is to making us understand how we can modify the binary and repack back so that it can be made capable to flash back. So this time, if you see, we do not need to go into this file extracted by Binwalk. We have this FMK folder. So if you look inside it, FMK, you have this rootfs. So it's that same squashfs file system, root file system, and we have the same file. Now, if you do the changes over here inside this, because if we do changes in that, there is no way to repack it. So I'll do same changes inside this sudo vi /etc shadow. So so this is what I had changed over here in the Binwalk thing. So I'll again do anything. So escape colon W. So you saw this change. Now we can repack this. How? We need to go back to our where is our FMK, and then we have, like, there is a command called build dash firmware.sh. I hope you all got this. Can you use Binwalk to go backward to binary? No, Binwalk cannot help us in uh, going back to the binary form. If it's not signed though, and you do not do it correctly, it won't. So we use this FMK. I hope everyone got these commands, no issues. If anyone is having issues in the commands, please do let me know in the chat so that I can put it there. Yeah, cool. So now to repack this binary, you have to use this build firmware.sh command and give the path of this FMK file. So it is /FMK. So it's repacking it. So now if you check, you got a new firmware binary, new dash firmware.bin. So now if you want to cross check that whether the change that you had done is properly implemented in this binary or not. You can just do it by extracting this new firmware and you can cross check. So let's do it. Now for just extracting purpose, we can use any tool. Repack command was build firmware.sh and the file name. Am I going fast? Yeah, I'll take a bit slower. Yeah, thanks for the review. I got this error, new firmware. I hope you are giving, Ahmed, I hope you are giving right path of FMK. So for example, if you are doing from full build command, it's like build firmware .sh and the file and the FMK that whatever. So I'll do build firmware.sh and path to FMK. I just hope. No, since we are if you are trying flashing, it might fail and you would have to recover the device somehow break. Yes. So when in this case, this is helpful. So for example, if you go to this file system, you have, let's say, sure, let's go to FMK. So this, we have tested on some of the devices where the secure boot proper implementation was not met. And in that case, what happened? In that case, what happens? You have to do just one bit change. So let's say telnet is disabled using telnet and it is zero. It's zero corresponding to it, like it's disabled. So what we do, we just turn that zero into one and then repack that. So in that case, it does not it accepts the flashing properly. So this we have found in most of the devices in which we were able to patch this thing with this thing. So if you look at, let me do anything. So regarding the compression, it is having like a Huffman compression it uses. So if you all are getting error, so it is placing the new firmware inside FMK because we are currently in the FMK directory. So let's see. So just let me take it a bit slower. I'll take this again. I'll take this again so that it gets more clear. So let me know if I have to repeat lab 1 or lab 1 is clear to everybody. The lab 1 we did. Yeah, lab 1 is good. All right. So let me take lab 2 again. So it should be a bit more clear. So I'll remove everything from here. So there's our so we have this directory. All right. So we had already seen that from Binwalk, though we were able to do the changes, but packing it back was different, was difficult. So for that, we use this tool, FMK. So I'll just we'll do extract this using Firmworker. Extract firmware.sh and the file name, binary name. I'll put this in a chat. Oops. So first you have to extract using the Firmworker tool. Extract firmware.sh and file name. So the very first step to pack with the FMK tool, we need to first extract with the FMK tool. All right. So you have to use this command and use FMK tool to extract it. I'll just extract it. So it takes few seconds. Yes, I can use Binwalk to extract, but the problem is our task is that we need to repack back. So if I extract with Binwalk, then the FMK is not in that, the file system is not in that format that will repack back. So to repack this thing, we need to use the FMK tool to extract and repack back with the FMK tool. All right, so I hope this thing there. So we are now, I hope everyone got this FMK directory. We will go to this FMK directory and you see the root file system. We will go inside this root file system and you can get all this file system that we had general. So now our task is that we want to change somewhere. So I can do, like, we can do change anywhere. So let's say I am doing this time. So cat etc, let's say password file, anything. So you have something in password looks like this. So what am I going to do? I'll just sudo vi etc password. You can do change anywhere. So it could be more applicable in some cases where you are doing changes in some configuration file. So if we take time bit to reverse this file and find that where this telnet service is being enabled or disabled. So making 1 to 0 or 0 to 1, you can make some service enable or disable. So similarly, you can, if the, let's say some word is written that is of size that is having 4 character, we can replace with similar 4 character to make the size same. So this changes. So let's say I'm doing any random changes, again, anything. So I'll just save this, right? So this is, if we check back, you get this. Now our task is to repack it back. Like we have extracted it, we have changes. Now we want to pack it back. All right. So what we'll do, we'll go back, since everyone was confused why it is in FMK directory. We will go to our lab directory. Now we are out of FMK directory. All right. We are not into the FMK directory. Now we will pass the build thing. So dot anything build firmware.sh, and then we'll give the path of our FMK. I'll also put it in the chat. So so if it is where is this? it is, so I'll just put build dash firmware dot sh dot slash fmk. Yeah, we do this. So basically the min functions uses, like if it is giving size related error, then we use that min option. When it gives the size related option, then we use this min option. So okay, it's saved to this thing fmk dot firmware, new firmware dot bin. So it could be inside this tool to save it. It has a path to save this. So if you run this command build firmware dot extract from the fmk directory, it should not give you that size related error. It should not give you the size related error. But if you are running from outside the fmk directory, then you need to give this dash min option. So this time we have, I hope everybody got this new firmware dash bin. So we can now to check it. We can now extract and see. We can use any tool to extract. We had done changes in, I suppose, password file, right? PASSWD. Yes. So if you look, you get what the change you have done in your new firmware binary. So this is the tool that that helps you in like repacking. If you are trying to repack something, so this is something which helps you. So yeah, so when the yes, again at some, so if we keep the size same, so it should not affect the checksum, but if we vary the size, it may be rejected by the device. Since there are chat and thing mixed, so if anyone is putting the question, just do one thing, you just put question and then put your question, so it becomes more clear to me that whether it's the general chat or whether it is the question. So if anyone is having issue in this thing, or shall I proceed to our next lab? Yeah, thanks for your. So I'll just check what's our next lab is. So even if someone face the issue, don't worry. What I'll do, while sharing the slide, I'll also share the lab steps. So that would be easier to you in case you want to practice a bit later. So now the next thing comes, crack the password. So we know that in the Linux we have that shadow files that contains des passwords in etc shadow file. So in this case, our task would be identical somewhat to previous one, to extract the binary. And after extracting the binary, our task would be to crack the password inside the system. And to the moderators, if there are any, just in case any chat that is that is related to the present lab that I'm doing, so please let me know like on the spot. But if it is some general, I can take on later also, so that if someone should not lag back in the lab at least. So we'll go back labs again, and we have lab 3. Yep. So we have our binary. I hope you all can now extract the binary by yourself. So our task is, we need to extract the binary. We need to get the firmware, and like in like this system file passwords are stored inside etc shadow file, that is like dash encrypted. And for that, we will be using the tool John the Ripper. So I'll just do Binwalk -e. So someone had asked significance of SquareFS file system. So there are different file systems used, like GFFS, SquareFS. So again, it depends on the kind of application that is being developed. So since I didn't download different binaries. I was trying to play around with one binary, and that's why you can see one file system. Some can have CramFS, some can have GFSS. So Binwalk is having like plugins for everything. Like they support GFFS, CramFS, SquareFS, so it helps you in extracting all those things. But for that, you need to do Binwalk installation properly in your machine. They have Reform Labs Binwalk installation page where they see this, like mention the steps clearly. So we'll go through this. Yeah, same steps. Cat -etc shadow. So there is this something, there's a root user, and to this it's the containing password, but we need to like somehow crack this, what the possible password could be. So we have a tool, John the Ripper. So you can also read more about on it, how does it work. So before that, we want to crack pass.wd file. All right, this file, shadow file, we want to crack the password from this file. So let's take it out from this and copy in our main directory where we have stored the password list. So John the Ripper has different ways, so we are using the word list method. So we have this stored password list which we will be using during our crack. So let us copy the file from etc, the SquareFS. Inside etc we had shadow file. So I'll copy it here. So you can now see password list and shadow. So we'll just use John command, our file name, and the word list that we are providing to it. Word list equals to, so I'll put the command in the chat also. Yeah, John the Ripper is a very good tool that are used by the hackers to crack the password. It support many. No, this is not dictionary based attack. They are. They have three different ways in which they do. I'm also not very in depth of like how they exactly, but it's not a dictionary or brute force thing. It's not. It's not dictionary. So you can do cat password list. You will get so cat password list contains general default thing. So the password command I'll just put over here. John shadow file dash word list equals to password dot list. Yes, if you do without giving this password file, it will take lot of time. So this standard password file are also present online. So you do, there are some very default thing passwords that are generally present inside it. I hope you all, so yeah, last what we had this. So if you check here, so if you see for root user, you have this password. So it was able to crack your password in few seconds, right? So this is how, so this is helpful when you are, let's say via hardware, uh, uh, I got no password. If you don't run as sudo, it won't work. So yes, so if it has been tried one time, so it sometimes create a default file inside this. Ls dot slash dot geo. So they are default pot files. So it does not work if these are so. Before, if you are getting error, try to remove these files from here, and then then probably this should run. So you should get something like this. So for the root user, you'll get the corresponding password. Yeah, so show password is basically sometimes what people do when there are many passwords, they save it in a file, and then we use dash show to like give that representable form on the screen. So let me know if I can proceed to our next lab. We just have, I guess, few 20 minutes, no, 15 minutes left. Yeah, so our next lab is more into dynamic analysis. So till now we saw some of the basic examples related to static analysis. Then we come to dynamic analysis. So in this case, what we'll do, we are having we'll be giving the binary, and we need to identify the custom binary. Sorry. So we need to identify the custom binary. We need to emulate it. Since we don't have the hardware, we just have this firmware. We will be emulating it and try if we can put any random data. So I'll just share. So let's go back to our labs. Lab 4. I think I can just remove. So this is through Binwalk. So I'll just, if you want. So you could be looking these files in your thing. So again, our task is to extract this. So we get into the file system. We get into. So our task is we want to emulate the binary. So to test our thing, what we do, let's emulate just the busy box. So the busy box that is present inside .bin busy box. So it's like the standard binary that generally contain all the different services inside it. So what we'll try to do, we will try to run this binary. So now if you try to run this binary just like this, so let's check if it, so it says no such file or directory, like it's, and if you check the architecture of this file busy box, sorry, it should be dot. Yeah, if you check the architecture of this file, it is MIPS architecture, right? So we need something that can emulate the file of MIPS architecture to our x86 architecture. So for this we have KMU. So one way to do is, if the KMU is already installed, what you can do is you can just do which KMU MIPS. So we'll do use MIPS static here. We'll use KMU user mode emulation. When I say user mode emulation, it means we are not providing any new kernel image or like a full system image to uh, boot up with a whole complete system, but we will use just this directory squash fs root system, and when we use chroot space dot, that would take this directory as the virtual host directory, and then this would in the backend forward the calls, system related call, to our main host. So for this we need to port KMU MIPS static inside this folder, inside this, or in. So what we'll do, you just need to do which KMU bin user bin MIPS static. You copy this path and copy this file into this directory. All right, we got this thing. So we got our since it is, why we are taking KMU MIPS, because our file is of MIPS architecture, and if it would have been ARM, we would have taken KMU ARM. So now our next thing would be, we will be doing chroot space dot. So chroot space dot means I want to do the root to this directory, dot means this present squash fs directory. Then we will pass this KMU MIPS, and then the binary we want to emulate. So let's say we want to emulate busybox. Sorry, it need sudo chroot. So you can see that my busy box is running. So it shows what's inside the busy box and everything. So if for people who have been able to do this thing, it means your KMU setup, like user mode setup, is working fine. Yeah, so if it worked good, now we'll just move our main attack. So as I had said we had to explore inside this file. So since we have less time, I would have told you to look inside the file, but I'll just directly tell you the file location now. So the thing is, there are many binary custom binaries. So you can either look into bin file or the sbin file. So let's list the file inside sbin. So sorry. So if you look inside the sbin, there are many different binaries inside it. So there are some custom binaries like k keeps reconnect, k keeps seek y, and k keeps on. So if we don't know the binary, our task generally is that whatever suspected binary that we find, we emulate it via KMO. So, but today I'm telling you that this is the suspected binary because we have less time. So, but if it would not, so we would have tried on different binaries to by running it with KMO to check if it is giving something or listening on some port or not. So now our task would be to emulate this binary using KMO. All right. So we will use the same command as busybox, but instead of busybox, we will give the path name of this file. Kkeeps seek Wi-Fi. So when you run this binary, you will see something waiting for connection. It means it is listening for something. It means if you check, let's check our let's start to check if some port is running or not. So if you check on using the netstat command, you will find that this KMO MIPS that we had run is listening on this port, right? Because this application. So though this application is running, but why is it showing here KMO MIPS? Because this this is being emulated using the main thing in the for the main host machine is KMO MIPS. So it is telling you that it is listening on this port. Now our task would be to try to send using this port something to this application and check if it is listening or not. So just to, let's say, echo random hackaday anything, and we'll pipe it to netcat, let it quit in 3 seconds, and local host and our port number that we saw over here, that is 58009 in my case, 58009. If I do this, you see this message is received over here, right? So what your next task would be to try to send different types of data through this. Try to mutate this using tools like Redamsa and send any kind of thing and check if this application crashes somewhere or not. Uh, can you listen to me? I'm getting some message on Hackaday, some Zoom related. Yeah. I hope everyone. So this is how you can try on these stuff. Just so we have 7 more minutes left. If you have, yeah, this workshop room is closed. So we are done with the labs. So if you have any questions, do let me know. Or you can also ask me via the public chat. What was echo? So echo was just for me to like to send piping. I was echoing and then piping the same thing to our netcat thing. So I can respond by public chat and will also send this thing uh, lab step by step and the presentation. Probably Sophie on the public chat itself, or have to mail you.
You can email it to me, or you can just add it to the project yourself.
Okay.
You're a member on the project, but if it's easier for you, just email it to me and we'll add it.
Sure. And thank you everyone for listening me.
Thank you so much. We are so happy that you came and gave this awesome workshop.
Yep. So this was very basic that I told you all, because if you are good at binary reversing, so this first initial steps help you in taking forward your next steps, like reversing those binary and how to deal with it. So if you are able to put it, I just hope I could have shown you the Gaidra one, but unfortunately not. But still that I'll try to put in the doc.